Hello, pre-calculus class. In this video, we will look at how to kind of piece together the last few videos that we did, the last sets of notes on the introduction to logs and the properties of logs, and kind of put it together in a synthesis and use it all in order to actually solve equations using logarithms. A lot of this really is not pre-calculus or involving logarithms. Probably the most difficult part of any of these types of problems is really the algebra, is kind of where people tend to get tripped up, is what I find. The logs piece is a pretty minor part of solving each of these types of equations. So yeah, we're going to do 3 different examples for this. A couple of examples that we will look at are ones where there is some unknown up in the exponent there. So like this example here, we have 2 times 8 to the power of 2x minus 4 minus 48 equals 2000. The thing that we're trying to solve for, ultimately, the x is up in the exponent. And we can use the properties of logarithms to get that out of the exponent in order to solve this. We'll do another example where it's a logarithmic example, like it's written as a log function where the x is on the inside of that argument, and we can use, again, the properties of logs to rewrite it to get x out of that, to kind of isolate the x by itself. So yeah, here we go. Like I said, one of the more challenging pieces of this, I think, is really not the pre-calc stuff, but just the algebra, right? Like taking a look at this big long equation and just trying to say, hey, I need to do the same things that I did back in Algebra 1 when I was taking that class first, right? This is just an equation where I'm trying to solve for x, right? And so I'm going to do it just like I always have by kind of doing that reverse order of operations, undoing the things in order to that reverse order of operations to get that x by itself. So the first thing I would do in this case is add the 48 to both sides, right? Addition is kind of the weakest of the PEMDAS orders that we have going on here, so that's the thing that I undo first, and so I end up with 2 times 8 to the 2x minus 4 equals 2048. And I can't combine the 2 and the 8 here because, again, order of operations, my exponents come before that multiplication, right? So in order to undo that multiplication, right, that would be the next thing in this order here, is I'm going to divide both sides by 2. And so that's going to cancel here, and I'll be left with 8 to the power of 2x minus 4 is equal to 1024. All right. So now I've kind of run out of algebraic things to do that, from Algebra 1 and Algebra 2. Now is where I would have to use this property of logarithms, right? Like I have this thing that I'm trying to find, the x value up in the exponent. So there are 2 different ways that I can get it out. I'm going to do both of them. We'll kind of do maybe the one that you possibly have even seen in Algebra 2 before. One thing that you can just do is take the log of both sides, right? So take the logarithm of both sides here, and I would get the log of 8 to the 2x minus 4 is equal to the log of 1024. And now I have the log of something to a different power. That is my power property, right? That says that if I have the log of something to a power, I can rewrite that with the power out front. Right? That will let me get this x out of the exponent and kind of down into the normal place where I would usually see it. So I can rewrite this as bring that exponent out front. I can bring the whole 2x minus 4 out in the front of this. Right? As 2x minus 4. Again, make sure I keep that all together because that's all in my exponent. But that times the log of 8 is equal to the log of 1024. That's the only pre-calc piece to this. Everything else is algebra. Because now again, I have the x where I would normally see it, and I need to continue to undo everything away from it. So the next thing I will do, just divide both sides by log of 8. Right? So divide by log of 8 here, divide by the log of 8 here. That's going to cancel that. And so I'm left with 2x minus 4 equals the log of 1024 divided by the log of 8. And this I can just plug into my calculator. The log of 1024 divided by the log of 8, that's just a number. So 2x minus 4. I don't have my calculator in the OneNote here. If I navigate away, it will kill the video, so I will just be your calculator for you. Log of 1024 divided by the log of 8 is 3 1/3. Get 3.3 repeating forever, just 3 1/3. So now add 4 to both sides. 2x is 7 1/3. Divide everything by 2, and I get x is 3.6 repeating, or x is 3 2/3. Again, if I had a calculator in the screen, I would suggest to you to take that 3 2/3 and plug it back in up in the original equation up here, right? Plug that 3 2/3 in for x there and actually evaluate and make sure that you are getting the right answer there. But again, I told you there was a different way to do this that I think is useful to see. Another way you could do it is to kind of go from this step, and you can really bypass all 3 of these steps as just one, right? Say if I have that 8 to the 2x minus 4 equals 1024, that's in that form, like right, a to the b equals c. I can just rewrite that in logarithmic form as the log base a of c equals b. So I just want to rewrite that whole thing in log form, which would be the log base 8. 8 is the base of the exponential, so it stays the base of the logarithmic function, of this 1024 is equal to, right, the exponent here is my 2x minus 4. Right. So just, I can rewrite that. And then this, you can also just plug right into your calculator, right? Desmos has that log base button feature, so you can just take this and jump right down to that step and kind of skip all 3 of those. So it's up to you. That's another way you can do it. I think this way is much more efficient, but if you like to just take the log both sides and use the properties, that also works. So either way, you should get the same answer. All right, let's look at a second equation here. We'll do an example 2. So we're going to have, this one we'll write in log form to start. We'll have the log base 3 of 5 minus x plus the log base 3 of negative 3 minus x equals 2. All right, so this one is a little bit different. Right, this one, we have the x inside of the argument of the logarithm, and we need to kind of work to get it out of that. Right here, x was in the exponent, kind of a tricky spot. We use logs to rewrite it so that it's just floating by itself. Here, we're going to, again, rewrite this thing. So we get x kind of outside of the argument of that logarithm. So I see the x in 2 different locations right now, right? But I know I have the log of something plus the log of something else. So I should be thinking right here, this product property, right, that we have. That says the log of a thing plus the log of a different thing is equal to the log of those 2 things multiplied by each other. So I'll take that and rewrite this. I'll have the log base 3 of 5 minus x times negative 3 minus x is equal to 2. Just rewrite using that product property. 2 different places I could go right now. I could FOIL this out inside the argument, or what I'm going to do instead is I'm going to rewrite this again in exponential form. All of these things kind of flow through that lens of, right, that if I have the log base b of a equals c. That is equivalent to saying b to the power of c equals a. C is the exponent, b is the base, a, the argument of the log function, is the answer to the exponential. And if I do that here, I can keep my base the same. 3 to the exponent is the logarithm to the second power, 3 squared, is equal to the argument of the logarithmic function. Welcome back to algebra again, right? The only new thing that we have here is just that rewrite, right? Using logs to take this and rewrite it like that. And now, again, it's a complicated algebraic expression. We got a quadratic here. We're going to need to FOIL that. But it's back to algebra 1, algebra 2. So let's FOIL this, right? First outer, inner, last. Right? Double distributive property. 5 times -3 is -15. And I'm going to write that one step down here. Right. 5 times -x is -5x. X times -3 is positive 3x. And then x times -x is positive x squared. And so that's all equal to my 3 squared, or 9. So, again, I always do my foiling like this because then it looks like a little smiley face, right? So that's just me. This is just a quadratic, right? So how do I solve quadratics? One way, probably easiest way, is to set it equal to 0. So I'd have to subtract 9 from both sides, right? Combine them with like terms, so I get 0 equals -15 minus 9 is -24. I got my like terms here of -5x plus 3x. It's going to be -2x plus x squared. And I don't like looking at it like that. I'd rather write it in like that polynomial form with the greatest power in front. I'll just quick rearrange this. Got x squared minus 2x minus 24. All right, so solve for x. I can use the quadratic formula if you want to, or I'm going to factor this because you are sophisticated math students and you should be able to factor these kinds of things. Right? So I'm trying to rewrite it basically so it's like something like this, right? It's got to be x and something and x and something else. And these two things need to multiply to -24 and add together to make -2. Right? So a couple things multiply to 24. I got 12 and 2. They should be opposites so that they multiply to a negative. That's too far apart. 6 and 4, that's going to work. Right? If I have x minus 6 and x plus 4, -6 times 4 makes -24. -6x, positive 4x will make that -2x. So 0 equals this, my zero product property. I know that x equals 6, or x equals -4, right? If x was 6, 6 minus 6 is 0, 0 times anything is 0. Or if x was -4, -4 plus 4 is 0, 0 times anything is 0. So there are my two solutions to this problem. But one of them is fake. So we need to go in and I need to check these solutions. You should always be in the habit of checking your solutions to see which ones work and which ones don't. So let's check this x equals 6 solution. And I need to go all the way back up to the very first thing up here. I need to come to this first piece one last time to try to copy it. Right. Don't check it somewhere down here, right? If you checked it in a different location, it's definitely going to work. I need to go back to the original equation and see, right, if I put 6 in for x here, is it going to work? So let's substitute in, right, 6 for x. Right, so log base 3 of 5 minus 6, so that would become the log base 3 of -1 plus the log base 3 of negative 3 minus 6 is a negative 9 equals 2. So then this, what is the log base 3 of negative 1? Well, again, this is looking for, right, if this had an answer, the log base 3 of negative 1 would be equal to something, would mean that 3 to some power would be equal to negative 1. Like 3 to the x equals negative 1. That can never happen, right? Like if you have an exponential function, right? We just looked at the exponential functions, right? Exponential functions, a property of them is that they have an asymptote, right? So if I had 3 to the x, that's going to be something like this. And if I wanted to find out, like, hey, where does that equal negative 1? That is never true. It's never equal to negative 1, right? So when we talk about logarithmic functions in the next video here, we will kind of discuss that domain of a logarithmic function. You cannot put anything negative into a log function. If you graph it, right, the domain of log functions is always positive. It has to be something like this. You can never put negative things into a logarithmic function. So if I get a negative answer or a negative argument for the log, that's not possible, right? This is an impossible thing. So that x equals 6 doesn't work. All right, sorry. Let's try x equals 4. So again, I've got the equation. I want to check it in this very first equation here, right? Where I'm going to put in not positive 4, but negative 4. Right? I'm going to replace that, my x's, with negative 4. So it's 5 minus negative 4, or negative 3 minus negative 4. If I do that, I get the log base 3 of 5 minus negative 4 would be 5 plus 4 is 9, plus the log base 3 of negative 3 minus negative 4 here is negative 3 plus 4 is 1. It's equal to 2. This, the log base 3 of 9, is looking for the exponent in the power of 3 that would equal 9. That's 2. This is saying what's the exponent in the power of 3 that would give you 1 as an answer. Again, from algebra 2, anything to the 0 power is 1. So, and that means that the log base anything of 1 is 0 every single time. So I'll get that is 2. That one checks out. So x equals negative 4 is my only true solution here. Right. This x equals 6 is said to be an extraneous solution. The algebra works it out so that it kind of comes out because, again, it would technically satisfy this, right? Like all of this, right? Even if I go up to this point, if x is 6, I will get 9 as my answer here. But the individual arguments, and even if I put the 6 in here, right, I will get 9 as an answer here. But when I go back to before I put those two things together, I would end up with negative things here. It works because a negative times a negative makes a positive, but that 6 is not a real solution to the original equation there. So always have to check for those, right? And I did have this originally as a little bit simpler one. It's like x minus 5 and x plus 3. X, yes. But that made the negative one be the extraneous solution. I really want to hammer home, it's not that the x is negative, right? Like that's not what makes this be an extraneous solution. What makes it be an extraneous solution is that the argument of the function is negative. And in this case, the positive value of x makes negative arguments for these logs, and that doesn't work. So always go back and check. Don't automatically throw out the negative one, but check it and make sure like what works, what doesn't. All right. So one last final example here that's a little bit trickier. All right. Final example. So here we got 2 times e to the 2x plus 5 times e to the x equals 12. So this one is a little bit trickier yet. Right? It all kind of rides on this piece here, and this will be like a bonus question on the assessment. So if you are not interested in doing that, you can tune this out right now. But I think it's fun and interesting to try to solve for this. So this e to the 2x, right? Like I need to find a way to be able to like combine this or get it into one exponential, because like there's no way I can rewrite this as it stands. I need to have, right, something to some power equal something for me to be able to rewrite it as the log base a of b equals c. If I have two separate things that, again, I can't really combine in any way, right? I can't just rewrite this in log form. So everything is hinging on this e to the 2x, right? So that e to the 2x, and normally we don't go this way, right? But if I have this written, right, let's flip this around. I could write that as the e to the x times 2. And again, one of those properties of exponents, of exponential functions, is this power property, that if I have, right, like x to the a to the b power, that's equal to x to the a times b. Usually we go from this to that, but in this case, we are going to need to go from this side to that side. This is equal to e to the x squared, right? Two exponents multiplied together is the same as one exponent, like with the base raised to the second exponent. So that's what I need to do here, is I need to replace that e to the 2x with this e to the x squared. So once I do that, then everything goes fairly smoothly. If I have this, I have then 2 times e to the x squared plus 5 times e to the x equals 12. Now we're going to do just a little substitution. I don't need to do this, but let's just say I'm going to let e to the x, I'm going to replace that, let's say with, well, let's just replace it with x, right? A little mathematically weird, but follow through with me. If I do that, then I would get 2 times x squared, right, plus 5 times x equals 12. Right? This is really just a quadratic with e to the x as the variable. So solve this like it was a quadratic, right? I'd have to subtract 12 from both sides, set it equal to 0, so I get 2x squared plus 5x minus 12 equals 0. Right? So I could use the quadratic formula, or I could factor this. Right? If you use the quadratic formula, you got your a is 2, your b is 5, your c is negative 12. Right? So either way, right, I'm going to skip ahead here because this video is getting a little longer. But if I do this, my solutions, right, quadratic formula, the solutions are that x equals 1.5 or x equals negative 4. But again, those aren't really my solutions here, right? Like it's not what my x is, because I made this little substitution here, which is really pretty mathematically suspect. So let's just go back and change all of this. Right? This is really a quadratic with e to the x as my solution. So I'm not getting x is 1.5 or x is negative 4. I'm getting e to the x is 1.5 or e to the x is negative 4. It's a quadratic with e to the x as my variable. So now I have that log function. So this I can rewrite as the log base e of 1.5 equals x, which the log base e is just the natural log, right? One of those ones that comes up again and again and again. Or, right, the log base e of -4 is x, or the natural log of -4 is x. Again, just like the example we did before, this one doesn't exist, right? I cannot take a negative number on the inside of something. If I have this e to the x function, right, e to the x looks like this, it will never equal a negative value, right, where y is -4 down here. That does not exist. You could just say that right from the get-go here. So this natural log of 1.5 is your only solution. So these take some practice, right? Like these types of problems take some practice. Again, one like this, that's going to be a bonus style question on an assessment if you see it. But these ones, right, like it's just repetition of getting, okay, I see that this is a log plus another log that I'm going to rewrite with that product property, and then getting everything. Like once I see the log base something of something else equals this, like I can rewrite those. So it takes some practice. So yeah, I think definitely the most important assignment in the book is in that section 7-5, right? The questions 35 through 45 or 47. Yeah, make sure that you work on those, ask some questions in the Teams channel, show up for the Zoom call, and I will see you later.